reactivity of the 5-membered ring heterocyclic compounds. So at the end of the session, you should be able to explain why the 5-membered ring heterocyclic compounds are more reactive than benzene. You should be able to arrange the furan, thiophene, and benzene and pyro as well in their increasing order of electrophilic substitution reaction. Then also you should be able to explain the 5-membered ring heterocyclic compounds, why they undergo electrophilic substitution reaction at the carbon number 2. So to begin with, we look at the electrophilic aromatic substitution reactions of pyrrole, furan, and thiophene. Now, because the 5-membered rings are also aromatic groups, they also undergo electrophilic substitution reaction. However, they are all reactive than benzene towards an electrophile. And the reason is the fact that the heteroatoms are able to easily donate their unshared pair electrons into the pi cloud of the ring, making the heteroatom relatively electron deficient and increasing the electron density on each of the carbon atoms. So let's use the pointer. So you can see that the pi electrons are being donated into the ring, making the carbon atoms electron rich and the heteroatom rather electron deficient, right? So the negative sign is always moving around, making the aromatic ring more electron rich towards an electrophile. So the order of electrophilic substitution we've already talked about, the fact that all these heterocyclics are more reactive than benzene, but however among themselves, which is more reactive? Now, furan happens to be less reactive than pyro towards an electrophile because the oxygen is strong, very highly electronegative atom than nitrogen. So as a result of that, oxygen does not effectively donate its non-bonding electrons into the ring. So between the two, between furan and pyro, oxygen does not donate its electron easily into to the ring, making the ring electron rich. So it makes oxygen less reactive than nitrogen. Now, thiophene has its non-bonding pi electrons in the 3p orbital. So if you look at the orbitals between nitrogen, oxygen, and sulfur, realize that the non-bonding electrons in nitrogen are in the p orbitals, and then the non-bonding electrons in oxygen as well as the p orbitals. But in sulfur, the non-bonding electrons are in the 3p orbital, right? So here it's 2p, 2p, 3p. So it makes it unable to overlap effectively in its pi bonding, right? And as a result of that, it makes it less reactive towards an electrophile. So its electrons do not easily overlap in its pi bonding orbitals to form strong bonds as compared to nitrogen and oxygen. So as a result of that, thiophene happens to be the least reactive, right? And pyro, because furan is more electronegative and unable to release its electrons into the ring, making the ring more electron rich, also is less reactive than pyro because nitrogen's electrons are easily donated into the ring to make the ring electron rich towards an electrophile. So pyro is more electronegative, followed by furan, thiophene being the least, and because all these three are more reactive than benzene, thiophene, as expected, will be more reactive than benzene. So the next thing is to look at the reactive sites on these rings, right? So if you look at the three heterocyclic aromatic groups, their reactivities towards an electrophile have two key sites. You have the carbon number 2 and carbon number 3 positions. So regiochemistry of the resonance structures produced by both positions show that attack at carbon number 2 leads to an intermediate with the additional resonance structure, making this intermediate more resonance stabilized. So pyro, furan, and thiophene therefore undergo electrophilic substitution reaction preferentially as carbon number 2 position more than carbon number 3. So please let's take note of that. or electrophilic substitution reaction involving these heterocyclics prefer the carbon number 2 position to be attacked with the incoming electrophile. So this is a detailed mechanism between the two. So we realize that at carbon number 2 we have our electrophile coming in as Y at carbon number 2, carbon number 2, and carbon number 2 here. So we realize that the carbocation obtained by putting the substituent at carbon number 2 is more stable than that obtained by substituting at carbon number 3. So these intermediates, right, these carbocations formed are all stable than the intermediates or carbocations that are formed at carbon number 3. So you can realize that the stable here means this carbocation is stable. The stable here, this carbocation is stable, but where the carbocation charge, the positive charges on the nitrogen is less stable, right? So we have two stable intermediates formed at carbon number 2, whilst we have just one stable intermediate formed at carbon number 3. So it makes attack of the electrophile at carbon number 2 more stable than attack at carbon number 3. Now the next thing is to look at typical examples. So when bromine reacts with furan, this is the product that is formed. So please take note, it's a substitution reaction. So the hydrogen here is replaced with one bromine, and then the remaining bromine reacts with hydrogen to form HBr. Similarly, because here the attack, the two position 2 are all occupied, the substituent is forced to position 3, right? Our Br goes to position 3. So please let's take note of this. Now, it should be noted that carbon number 3 is also activated towards electrophile attack, and therefore mixtures of products can be formed depending on the reaction condition, the substrate, and the type of electrophile. Right? So depending on the reaction condition, some type of electrophiles, there are cases where the carbon number 3 position is the preferred position. But all things being equal, the position 2 is the ideal position towards any electrophile.